we are working over field F, whose characteristic is supposed to be non-zero. We are considering a quadratic form which is the following. So we have Q from V to F, and dimension of vector space V is finite. Then we have, this is a quadratic form which satisfies two properties, namely from S times B as the scalar S squared times Q of V. And the second property is bilinearization, 1, 2, Q of V1 plus V2 minus. This is a symmetric by definition, but it's symmetric R bilinear form. R bilinear. Then we introduce the concept of a regular quadratic form, which is the following. Is regular, meaning that the canonical map from V to V star sends a vector to the polar form where the first argument is fixed. This function is linear form. And this is always well defined for any quadratic form, and the quadratic form is called regular if and only if this is an isomorphism of vector spaces. This is the sign of love. And I try to convince you that regular quadratic forms are the quadratic forms to study. In particular, I mentioned the following very useful property, namely, you have an arbitrary quadratic form, and you have a subspace U such that the restriction of U to U, this is then a quadratic form on U. This quadratic form is regular. Then this implies that you can decompose your vector space with direct sum of subspaces U and perp, where U perp is the orthogonal space of U consisting of all these in V such that EQ of 0. So this wraps about up as well the essential point, and I'll start today's lecture with diagonalization. And it comes in two parts. Okay. Wait. Well, suppose we have a finite dimensional vector space V, which should have a basis chosen. So suppose E1 up to En basis of V. And suppose we have chosen arbitrary elements A1 up to En. Well, then you can define quadratic form on V. Then U V to F, which takes a vector summation I of 1 to N R I V I, states this vector to sum and then I take Ri squared AI. This function is a quadratic form. So diagonal form denoted A1. So this is a quadratic form because if you multiply here scalar b by j and s, it goes into Ri, then it goes up to the square. So all the factors have s squared. So at least it satisfies the first defining property. And it's a bilinear, it's a quadratic form because the BQ for this particular form of, say, R1 up to R summation Ri EI and summation SI EI. And if you work everything out, and what you get is the sum over I for 2 AI RI SI. 2 are AI are constant, so what you do is you consider this as a function of the RIs and SI instead as such a function, right? Right? So last time I also introduced orthogonal sums, so then this is just the orthogonal sum of this particular. Right? Now notice that this particular quadratic form has the property that if you take very special this particular group, if you work out what is EI EJ, right? Now if you look at here, this formula, see it's 0 I is right in this form delta AI here. Particular I is not j equal to j, then this is 0, so you have a orthogonal basis.
You have got your famous 2.
2 delta ij. Just checking if you are.
Yeah, exactly. Don't trust me.
Okay, so we see that every instance can be made an orthogonal basis for some quadratic form and for many quadratic form. And diagonalization says that the converse is also true in the following sense. If we given a quadratic form, arbitrary form, on Q, there exists an orthogonal basis for Q, i.e. actually for BQ, it says that BQ of need to make a main basis EI E1 up to N. If you look at BQ EI J, then this is 0 for J. And hence, consequence, this quadratic form then is just the diagonal form A1 up to An, where the AI are Q. So how do you construct the spaces, well, works by reduction on dimension. So we look at the full vector space V, and we distinguish two cases. So if you have case that Q of V is completely zero, then this implies that the monoform is completely zero, it's totally zero. And then any basis will be a thought. This is sort of stupid. Any basis to do. Okay. So this leaves the more interesting case that Q of V is not zero. So then that means you can choose an E in V such that Q of V is not zero. Okay, I'll call it A. Now let me look at U being the line through V. So that means all scalar multiples. Okay. So if you look at the form Q restricted to U, to evaluate the element R times E, what do you get? Well, this is A times R squared. Okay. But A was not zero. So last time we checked that this particular quadratic form on a one-dimensional space is regular. Right? So then we can apply our fact here, or our result here, follows that V decomposes as a direct sum dE and per. Now, the dimension of U per is just the dimension of V is 1, right? And either you have proven result for lower dimensional and you can use it, or you say, well, now I repeat this process for U per, and eventually you become surprised. Okay, so this is useful. And let me say it only works for a characteristic not true. It's not true in characteristic. However, in characteristic 2, for those who are interested in characteristic 2, can prove this that you can always think of, you don't have a general and orthogonal basis, but you have a solving sum of at most two-dimensional spaces. So that is the subset. Okay. Now, the main theme of today's lecture is phase change, going up and going down. Namely, which is here, what we will do is we will consider an extension field of that. Like, for example, F could be the real numbers, and extension field then could be. And what we want to do is we want to start this Q quadratic form over F. We want to move it up to K, quadratic form K. And then I will also tell you a little bit about going down. And we will consider a concept called lower time. Okay, going up. Which goes under the name B. Right? So let EQ be an arbitrary quadratic form. And let K over F be Q. Then the goal will be to construct quadratic form over K. Now, to construct a quadratic form, we need first of all a vector space over K. Then we define a map. Well, the vector space over K will be what is called a tensor product. Right? Define K is the tensor product over F. K. Now, I'll tell you a little bit about this later on. So this is a K vector space. And it is spanned over K by certain symbols, called simple tensors, which are B tensor, A, B. Now, the important point here is that so if you have a basis 1 up to the n, this is the basis of B. So B is a vector space over F. Then look at these tensors, one tensor, one K, n tensor one K. This is a basis of BK. Okay. Now, so that later on in the linear algebra course, you will get things, tensor products or vector spaces. So there's a whole theory which lies behind this. I will just use this particular fact in order to prove that we can construct quadratic form over K. Right?
Students will come a little later, but my lectures are on the website, and they know, and that is one of the things there.
Okay. So if we read up. Now, so this takes care of the vector space, right? We take this tensor product, we have a vector space. Now, I claim there exists a unique quadratic form Q, which goes from B to K, and it's unique by saying, well, we want to use our Q, so we say QK, the simple tensor should be Q of V times K squared. For all B and B and K. Okay. So first of all, this right-hand side of the definition, this makes sense in the following form. See, Q of V is a scalar in F, but we have taken a field extension, so we consider F as a subset of K. And so what we use on the this right hand side is we use the multiplication in the field K. So at least we have defined a function. And then you can so how do we define this function? At least I will show you. Distance. Okay. Well, we use diagonalization. We use the first part, like so. We choose from this. For that. So then we know that our Q has the following form, right? Q of a vector V, so this is Q X. I write my vector V in terms of my basis. I get I equal to 1 to n, or I in I. But then because this is a orthogonal basis, but this becomes is just the sum I from 1 to n, or I squared Q of. Now this is a polynomial in the Ri squared. But now what I do is I simply replace scalars which come from F and the scalars K, and I use the same form. So then fine. Use a K. Now I know that elements of this type are bases. So anything which lives this vector space VK can be written as a K-linear combination of elements like this. So I have a sum I from 1 to n of, well, the K scalar multiplication just works on the second factor. So I write this as TA tensor AI. I define this I equals 1 n. Then I say this should be Ki squared. Now, Q, because this is also on the basis, I would have Q of AI times 1K, but because of my requirement here, the K is 1, and this is 1, so I can just do it. And so at least we now know that this is a quadratic form, a quadratic form, by applying the first part of the this is obvious basis. Then you have to check that it satisfies. Okay, so we now know how to go up. We have a Q and we have to construct the quadratic form. Now you're in the position where I use sometimes, often, algebra. Whenever you have some object which allows base change, then it's natural and imperative to ask what are the relations, what are the good properties which are preserved by going up? Like, what is So we want to do is we want to relate properties of Q and properties of the extended form. And the first for example, you could ask, well, if I have two quadratic form over F, which are isomorphic, obviously they become isometric upstairs. Hey, you should ask, for example, well, so the first thing I would like to mention is an exercise. It's not very difficult, which says regularity is preserved. Namely, if you have BQ arbitrary quadratic form over F, then the following are equivalent. Number one, my Q is regular. Number two, QK is regular. For all fields. Okay. All fields. Number three, well, QK is regular for some. For A field. Right? And the most interesting of these three equivalent assertions is going from 3 to 1. If you know that you have a quadratic form which is regular over some huge field, then you can go down. So I won't tell you what is the proof, it's not so complicated. Okay. Now, the next item I want to look at is isotope. So recall we said that DQ is isotropic. If the quadratic form has a non-trivial zero. If there exists non-zero V such that Q of P zero. Okay. Now, question. You can now ask, how is isotropy related to base change? Right. So let's start with quadratic form, which is isotropic. Right. As up here. Okay. Now, we just rewrite this. We have a non-zero vector. Now, one properties of tensor products to set up is that if V is non-zero, then V tensor 1K is not zero. This is a property of tensor products. Chinese. So this is already good. And what is QK of Sweden and Toronto? Well, by formula here, it's now one here, that's which is 0. Right? So what we proved is that if Q is isotropic, then any base change does. So the question now becomes, well, can we go down? Say, I know that over some huge field extension, the form is isotropic. Is it already isotropic to begin with? Yes. Yes. Okay. But so let's look at simply basic extension. So take A, B, C complex numbers and F. So take a positive definite quadratic form. So recall that this means positive for every non-zero. And so because of this condition, positive definite quadratic form will definitely not be isotropic. Now, what happens if we go up to C? Okay. Well, get a nice regular quadratic form. Here. However, the dimension over R of V, which is then of the dimension of C over E times C, this is at least 2. That I said last time, using some heavy machinery like Nullstellen, that then Q of T. So we started with something which is not isotropic, and we concluded that there was an extension where the form becomes isotropic. This means, turning it around, we cannot go back. QK is isotropic, does not imply in general that Q itself is already isotropic. Perhaps this was not so surprising. However, let me state comfortable result. I hope you will find surprising, which looks at this particular question. This is called Springer's equal tension. It says the following, so given quadratic form in Q, and the field extension such that the degree K over F is odd. So odd degree extension refers to this. Then Q is isotropic if and only if the tip. Right, and of course, the interesting, we can do one easily, the implication from left to right. But the interesting fact is that when those from right can go down. So the proof is a little bit longer. It will take too long to prove it here, but it's not so complicated. Let me rather tell you a little bit about the name of this thing. First of all, this is a conjecture of Witt. Told you about Witt being the founder of the modern theory, great theory of quadratic forms, right? So he wrote this remarkable paper in 7, where a lot of his ideas, where he developed new ideas to look at quadratic forms. And as a side remark, he conjectured that this should be true. So some of you may have heard the name Artin. Two Artins, so this is the older Artin. Emil Artin was in Hamburg, where Witt also was. And Artin told Witt how to prove it, but Artin was too busy with other stuff. So he didn't prove it. And then the young guy, Springer, came around and he proved it, he published it. And so it's called the Springer's odd degree extension theorem instead of Artin's odd degree extension. Right? So, moral of the story for all the young guys, don't wait if you have a result, publish. Publish or perish.
Failures who themselves and steal older math.
Okay. Right. Now, this then says that we can go down for at least some nice extension of part. But I would guess that you will not really be so excited to say, okay, isotropic, that's fine, but what is so special about isotropic? So in order to convince you that this is actually an important result, let me discuss two corollaries of this result. So we will prove the corollaries first by using Springer's theorem in some intricate way. So we take K over F field extension. And we assume that its degree is odd. Now, question. You see, isotropy means, in fact, that there exists a non-trivial zero, a non-trivial vector, which is mapped onto zero. Right? So this deals with the value 0. But you could ask the same for a non-zero value. The following form. Suppose you have the non-zero A F. And the U F as a subset, okay? Then, if the A is value of some vector over F, then it will also be the same vector, K. But you can go down, namely, A equals Q sub K for some W. K, if and only if A already is represented by Q itself. For some. So not only can we go down, up, down for value 0, but also for non-zero state. For those who have been at the lecture sometime yesterday, this is one of the things which I use. Okay. Part B of the corollary says that take two, let Q and Q prime be regular forms. Over F. Now, if they are isometric over F, then you can lift the isometry to K. Okay, so if Q is isometric to prime, then it's clear that Q K is isometric. K the source of any K. But the point is that you can go back. Isometry is preserved by, you can, regular two forms are isometric over F if and only if they are isometric. So this leads to that. So I will show you the complicated how to prove at least the first.
Why is B not for anything? Like why is there the regular extension in B? B composes regular parts, the other. It's not centered.
Point is. So. Okay. So we want to make use of Green's theorem, and there is a nice trick. Okay, what you do is, when we have this A, we've given this A, then we form to the new quadratic form by saying this should be Q direct sum is minus 8. So this is a bilinear quadratic form on B prime, which is F direct sum is B F. And so Q prime of B comma some R, by definition is Q of B minus R squared. Can do this. Now I go to Q prime K. So taking tensor products from roots is direct sum, so the class will give a base description. So this is just QK sort of minus K. Now, I know that we have W K such that if you calculate that QK W is A. So now I can calculate Q prime W comma 1. And if you use the formula, then this is A minus A 0. Now, this is a non-zero vector. Use one component. So what this tells you is that Q prime K is prime. Well, because our field extension is hot, and then apply Euler's theorem says that Q prime is hot. Well, what does this mean? So this means there exists a V in V and an R in R, such that 0 equals V prime V from R, Q of V minus A times V. Now, if, well, first, this means Q of V equals A times V. Or if R is not 0, what you get is Q of 1 over R times V, which is R. Now, if R is 0, then what this means is that V is isotropic of the vector. And then there's a little device which which says that this implies that you have a hyperbolic plane sitting inside. The hyperbolic plane has the property that every element is represented. So what you get is that Q of zero, particular value as vector from the set. Right, I think this is a nice trick. The proof of P works a little bit more complicated, but it uses what is called bit cancellation theorem. And since I haven't not yet told you what this is, okay. So what we have done so far is we considered properties of quadratic forms of the K, trying to understand what is the relation quadratic form over Since we started with something down here and we moved up. Now, want to go down. So to go down, I need to the concept, which is called the norm, which I will now introduce. So we will always work with finite field extension. So if we read finite passwords, K considered as a vector space over F is finite dimension. Right? So for example, C over R is okay. But R over the rational numbers is not okay. So the idea is that there is a natural function which goes from K down to F. So the norm, it's called norm. The function K to F, and it's defined by mapping K, the determinant of the endomorphism, the F vector space K, LK is left multiplication by K. So this is the multiplication in the field K, but I can view this as a linear operator of the F vector space K. So LK is an endomorphisms over F vector space K, and have the concept of a determinant of such an endomorphism. So what you do is you fix a basis of this F vector space. You represent your linear map in terms of a basis. The determinant of the linear map is exactly the determinant of this particular basis. Right problem? So this gives us a well-defined function, and it has some nice properties. Well, you see, you cannot expect more than just properties of the determinant. The determinant is in general not linear, rarely linear, but it's at least multiplicative, right? So the norm, two elements, plus the product. Because the determinant of the product is the product of the determinant. Okay. The norm of 1 over K. So by definition, this is the determinant of left multiplication is 1, which is the identity value. So it is represented by the identity matrix. Determinant of the identity matrix is 1. Therefore, what this implies is that norm of a non-zero vector is also 0. Now, if you have an R in F, then you can multiply vector A R. And then this goes out, which is R D or the Z is just the degree of physics. Okay, so it has some nice properties, at least these properties. It's in a sense also a polynomial, but a polynomial of degree D. So now there are two principles for using the norm and quadratic forms. To draw. So because in the last lecture I told you that we can multiply quadratic forms by scalars. So we call A Q is a quadratic form. Then A times Q quadratic form F, which maps vector B, A times Q. Okay. Now, Gauss' own principle is the following. I should first say who is Schala. Well, Schala was one of the main contributors to the theory of quadratic forms in 1960, 1970, 1980. I think then later on he switched area. He became interested in history of mathematics, and he's famous for having written the biography of Hoyle. 3 volumes. So, okay. So we take K over F, a finite field extension. We take an X, which is in case times, which is K minus 0, go to X. Then we take Q, any quadratic form over our base for that. So then we can compare the extended form to K and X times Q. And it could happen that they are isometric. So form which is as to scalar times the form, this is called variable. But if this happens, then Q is already isometric to a scalar times Q is isometric the norm You see, the point is that this isometric is not true for any Goodloe scalar. It's obvious that the scalar, if the scalar is a square, then if this x is a square, then yes, there are symmetric, and the lower will tell you that this is obviously here. So the point is that this x is not necessarily a square. So this is Charlotte's law principle, telling you how to go down. I made okay. Now there is a second principle proven around the same. This was proven around 1970. Due to Knebusch lived at the same time. Charlotte, temporary of Charlotte, he worked a lot about students and great spectacular results. One of them is the following. So we looked at values of quadratic forms. Okay. And declare zero or so that there is a special name for the non-zero vector of values. This is q of v minus 0. So these are all values represented with f. Zero such that will be a sum. Of this is to go. This is the following. So, as usual, we fix this as a k over a field extension finite, and I denote its degree. Now we take any quadratic form. Then we can consider its values over k. So first move up from f to k, we get a certain subset, right? So, and of course also to k. This is to k of bk minus 0. This is a certain subset of the non-zero element of k. Can apply the norm to it. What you get is dq close. Don't get dq itself, but what you get is product of dq's that has d effect. So this is Nebuch's norm principle for values of the forms. It has important applications in something which is called spinor norm, definition of spin groups, special. So The proofs of those principles are somewhat more involved. The proof of Charles law principle uses what is called Charles transfer, which also then which in addition uses multiplication of quadratic forms. So, in the remaining 2 minutes.
No. 15 we go, right? It's 8 minutes.
Remaining negotiate.
Can negotiate more.
I will tell you about how to multiply. So, let me erase this because this. So, you take two quadratic forms. Over a base to F. Now, one can multiply vector spaces. We will learn about this later on in the course on advanced linear algebra. One can take the tensor product vector spaces. Okay. So, and the one tensor over F, the two is an F vector space. I claim there exists unique F quadratic form to one denoted to one two, which is find out the F vector space in one to two. And it's unique by requiring Q simple tensor. It's just product of the triple factors. Okay. Let me tell you a little bit more about what I'm doing while it's happening. You see, okay. So this tensor product is some gadget which is an F vector space. So the one tensor V2 as an F vector space spans over F of simple tensors. V1 tensor V2, the V1 is V1 V2. And so I say, well, this quadratic form is we describe what it should do on simple tensors, that because they span, they're not so surprising that if it exists, it must be unique. Now, the next fact is It's the one plus effect. That if you have a basis B1 up to the n basis of 1, F1 up to Fn is the basis 2. So they, here I sum up to n, here I sum up to n, so they don't have to have the same dimension. But what comes out of the theory of tensor products is that then if you look at all possible combination of simple tensors from your basis element. This is the I tensor Fa. The I runs from 1 to n. This one J1 from n. And this is the basis of the F vector space E1 tensor. So you know now what is the dimension. Dimension of this tensor product, just the product of the dimension. It's n times n. Times n. Okay. So now here comes the distance. Very cheap. And what we do is, of course, this works for any basis. So what we can do is we can take orthogonal basis. Okay, so take our orthogonal basis, which we know exists. One up to n. So then we can define, then applying this to a orthogonal basis gives us a basis EI tensor Fj of B1 tensor B2. And we have seen the diagonalization process, once we have a basis, we can arbitrarily define the quadratic form. So what we do is we define this quadratic form B1 tensor B2 on a simple basis element in the way it should be prescribed here. This is Q1 of EI and Q2 of. So this gives us a tensor product. This gives us a multiplication of quadratic forms. And to finish up, one can now check, does it have some nice properties? Right? It has some nice properties, like one associated. Transformatic. And it respects what a orthogonal sum. Etc. Right? This is what Witt, in fact, Witt knew. There are some more formulas, and this looks like associativity in a ring, and this looks like distributivity in a ring if you interpret orthogonal sum as a sum, and then this leads quite naturally to Witt ring, and I'll talk about this next time. Right. Thank you very much. See you. Bye.
If you are particularly interested in the intricacies that arise in characteristic 2, what is a good reference where this is treated in detail? quadratic forms over fields of characteristic 2.
There does not exist a book which is specifically for characteristic 2, but there is this book, which I think I wrote,
Yeah.
Hermann Courier. Okay.
Yeah.
And they make a point of developing quadratic forms in any characteristic. They go out of their way to the extent that they say sometimes in a proof, characteristic not true, here's the awful proof for characteristic true.
Okay.
There's also the book by, there's a little book by Neher, which is a translation of lecture notes Neher wrote in when he was in Göttingen, and that translation is done by Rudolf Scharler, the professor of the Scharler. This also gives us some nice results. This also has a theory of quadratic forms. But it also has something about local rings and semi-local rings. Beyond that, I mean, there's this book by Knus, but you know,
Emission forms over rings. Yeah.
And then you go to emission forms over rings. And there are the orthogonal papers by Knebusch. He tries to make sense, to prove results which are characteristic free. Then there is this lecture notes by Baeza. So he has he was a student of Knebusch. He has a Springer lecture notes devoted to quadratic forms over semi-local rings, which is his Habilitationsschrift. That's all.
The odd degree is just going to say it. This will to make a one is feels.
The odd degree extension theorem is the spirit of it just that you have an odd degree extension, either both fields have a square root of -1 or -2. Like this example where hard to see the news for gain isotropy being caused by the square root of -1, right? So we have a positive definite form over R, becomes isotropic over C. This is being messed up by optic, square root of -1, right? It's the troublemaker. And is the spirit of the odd degree extension theorem that when you have an odd degree extension, either both fields have I or neither have I. No.
It's not about this square root of -1 was for the existence of moments.
This is, there's nothing to do.
I guess if something is not a square in the base field, and it is a square in the higher field, it must just be an equal degree.
Here is the structure of the proof. I think it's
Sure, it might be proved somewhere, but morally.
the structure of the proof is almost the same for Knebusch theorem and for Scharler's theorem. So what you have is an element in your K, in your base field K. You get field extensions. Then there are these two intermediate steps, F is equal to FA, where FA is equal to K. Those theorems, FA is equal to K. This is the most difficult. This is the verb actually. So what you do is you see what is FA. This is just a polynomial ring. Modulo some item P. P and degree. You know. Okay. Then what you do is do an induction to show that if you have like some frequency and something that's dropping over K, with this assumption, then construct some extension of this form where the degree P is odd and less than if construct, if it's isotropic here, then you construct something, a vector space where it's isotropic here, and then you go down and okay, forgot to say the principle of Crookes that you assume that Q is not isotropic by contradiction. Not isotropic, meaning it's anisotropic, but UK is isotropic. And show that this cannot happen. Right? So what you do is Q is not isotropic, but your K is isotropic. In this case, lower the degree one step at a time for staying in odd degree. So eventually you run it. That's the idea. The Knaper-Stone principle is essentially the same idea.
Not directly contradicting what you said.
No, it's like it feels like I diagonalize my cube. It has some coefficients that define it. So the same coefficients that define UK. And so topic vector,
You have a zero.
right over 2K, there's a zero. That isotropic vector, is it true that it must involve elements which it feels like it should involve elements that are now squares. But
I don't know. You see, one block, one. So what I did in the proof of Springer extension here, seminal, say, okay. Have this isotropic vector over upstairs with K. I work with that particular vector. This is what I propose. Where it turned out that this may not be a good vector to work with. Rather, tries to prove that there exists a vector such that a certain coefficient is non-zero. And is in this case non-zero over a ring, it isn't good. So I mean, you know, algebra neutrality. So invertibility is an open condition, so there is some that you can achieve. So if you are in this situation, you see what happened is if you look at B tensor K, right, so this is B tensor A, right? So FA is free. So this is a direct sum. And write this as B tensor input. And you have a vector here sitting here. So you write your vector as the sum. Certain times T. Bi. Okay. A priori, you don't know anything about this except that Q of this is 0. But you're in business, it's straightforward. The main verb goes into this. If you know that to define n as the maximum, the highest coefficient, but if you know that Q of the n is a verb, it's not 0. So start with some vector, which is isotropy. You try to find a better one. Now this
One
one,
Q of the I. N is the maximum. Q of the
maximum. So the dm is the highest coefficient. This respect.
Oh,
So that's the idea of. So I don't see. See, if you wanted to write this in a different way, you wanted to use that.
Okay, is there any work then in the other, jumping into the wrong direction? Is there any classification or any statements stating which types of even degree extension solve this?
There's no classification. There are some theory.
Even degree extension variables?
Yeah, there's an example of 3-4 field extension. The screen is still. But it's a very stupid thing. These are fields which are quadratic fields, and so essentially every quadratic form is fine. So
I guess if you feel a base field for every that's a topic then. Right. So that are there non-realistic?
well, that's the only illustrated example I've seen. But there's no substance.
My guess is that it would be based on this DQ. Some relation between the coefficients defining Q and being in this DQ or not. Or something.
Okay. But to give some more background, okay, you can ask the same result based in quadratic forms in omission by omission. I think there are some examples where this is not always true. For the previous theorem, it's not true for omission. It's also not true for forms of higher degree. Right? So replace quadratic forms by cubic forms.
And then if your extension is not equal by 3,
But very few people understand.
because they're far from not interesting.
It's hard. Because, for example, see the quadratic forms are defined by being homogeneous of degree 2 and the total form. But cubic form should be a function which is homogeneous of degree 3. Then all sorts of linearization should be 2 or 3 by 3. There's several organizations.
Yeah, this. Polarization.
There are called polarizations in the theory of quadratic forms, the theory of geometry, linearization.
I don't know. What's polar about them?
It's also in many variables, it's called polarization too.
So
There must have been, yeah, so. Came from somewhere. Thanks.